Hello and welcome. My name is Reiner Stuhlfauth. I'm a Technology Manager Wireless of ROHDE SCHWARZ. And in today's short session, I'd like to touch on a few aspects of EMF, electromagnetic fields, with regards to 5G. So why do we need to measure EMF? Electromagnetic field is to measure and verify the human exposure. The electromagnetic fields, and especially to verify standards, to verify sites, and to make sure that we do not trespass limits to get a certain general acceptance. So when we talk about EMF in details, we see a certain influence on the human. Yeah? And this influence of the EMF, which leads then to regulatory issues, this influence is triggered and set by certain parameters like the frequency, the power density, whether there's a modulation on the signal, and how much or how long is the exposure time at all. That means the challenges in EMF, we have the simple physics, that is fact, but we have worldwide and even nationwide various standards and various procedures how to measure and now how to look into the EMF part. So I'd just like to show one single kind of guideline for EMF measurement exposure. There are 10,000s of pages of documents, nationwide, international, etc., etc. So this could lead for several weeks of webinars, by the way. So I only would like to touch down on here on the ICN-IRP, which is the International Commission of Non-Ionizing Radiation Patterns, yeah, and Protections. And they are writing a lot of standards and documents and propose procedures how to perform measurements on EMF and also what are limits and what are limiting factors. For example, we see one graph issued by the ICN-IRP, which is setting certain thresholds for EMF exposure. What is important for us in the wireless technology world is like here the blue circle. You see the zone in the range of, let's say, 100 megahertz to sub 6 gigahertz to 6 gigahertz range. And also here you see different curves which are defined by the certain exposure time, whether this is only a few seconds exposure or whether this is a 24/7, so general exposure. And we have different kind of limitations. For example, we talk about the SAR, the specific absorption ratio. You see here this photo of an artificial head filled with non-electric material, and then we measure the radiation, the power radiated into this certain artificial head to measure the EMF exposure, specific absorption ratio. In the table below, we have a general limit, a threshold that we should not trespass in any circumstances at all. So this is, let's say, the red line, and whatever happens, you should never trespass this limit for any kind of health issue. Then we see tables like that where we have the limits for EMF depending on the exposure time, whether this is only a single exposure, so occupational, or whether this is an exposure that is 24 hours, 7 days a week, so a public one. Also important to see when we talk about EMF measurements, depending on the frequency range. For example, in the very low frequency range, so here the standard says less than 10 megahertz, we have to measure the electric field and the magnetic field. In our typical frequency ranges used for wireless standards, so the 100 megahertz to 6 gigahertz, for example, we measure only the electric field according to the standards. And simplified saying, what we measure is not the field, we measure power. Yeah? So we have an antenna which has a known characteristic, so we know the antenna factor K, and we measure the power, the received power, and this power is then converted, you see the formulas below, this power is then converted into the electric field strength. Generally speaking, and this is an important message, we have two different ways how to measure the EMF. We talk about a frequency selective measurement and we talk about a code selective measurement. So what's the difference? In the frequency selective measurement, I don't care about the signal content. We have a spectrum analysis, you see it here on the left side, and we do a power scan over the certain bandwidth that we would like to measure, and we detect all signals. So every signal that is visible within this frequency band contributes to the overall exposure. The other part is the code selective. So in the code selective measurement, we have a specific signal typically a reference signal that we know the structure, and then we measure the power explicitly on this specific code signal. For example, the RSRP of, for example, an SSB block in 5G. From the standard, we have different ways how to measure, so different kind of setups, how to perform EMF measurements. I would just like to show a few examples. So first example I touched already. This is this very near field, so the reactive near field SAR. So typically measured in a lab, in a shielded chamber with this artificial head, with non-electric liquids inside, and then we have to do a lot of difficult mathematical calculations to emulate the free space resistance. Yeah? The typical EMF measurements, which is done on a fast show, is this fast scan. So typical with a handheld equipment, like here the FPH, a spectrum analyzer with a handheld isotropic antenna, and this gives you a single snapshot. The EMF exposure at this moment of time, at this position where you currently perform the measurements. This is mainly done for verifying a site very quickly to get a general impression how the EMF exposure looks like. A more enhanced level of EMF exposure is the transmitter site verification. So that means I have to prepare. I need a strategy. I know somehow how my transmitter looks like. Yeah? So we know, for example, about the technology, the antennas, where the transmitter is located, what is the exposure time, what is the direction of an antenna, for example, and then we build a strategy. Where we want to measure, how long do we measure, what test equipment is used to measure, etc. So just here a few examples. One example known already from the legacy generations, like already GSM, 3G, 4G, where we have a sectorized antenna that looks into a certain direction. So here it is obvious that I position myself with the test equipment into that kind of main direction of the transmitting antenna to emulate some kind of worst case condition. Furthermore, some standards require multiple measurements, so like a multi-point transmitter verifications. Here just two examples. Either you do this handheld antenna steering with your hand, you move in certain ways the antennas and you do a peak surge scan for the power level, or the other method is that you measure at different altitude heights. Or another kind of antenna verification is a kind of full site analysis, typically performed by regulators. They have to look into different radio technologies, they have to look into different standards, they have to measure the antenna site at different positions surrounding the antenna site and doing some kind of averaging and integration. And last but not least, also here one example, we also have permanent EMF exposure survey, like a monitoring of the EMF in a 24/7 period, so 24 hours, 7 days a week, you permanently integrate and measure the EMF. And this is typically done by, let's say, government agencies, regulators who are monitoring the EMF exposure on a certain site. So when we come closer into some 5G aspects, the first simple question means we talk about EMF exposure, but what do we measure? Give you a simple example. I assume I have here a multi-site. Yeah? Multi-site means there are several network operators sharing this site, so here the rooftop of a building, and we have installations of multiple radio technologies. There's, for example, a GSM antenna, a 3G, UMTS, a LTE and 5G. So now the question will be, what do we need to measure? Typically, the answer is, I need to measure the EMF on radio technology A from operator A. I need to measure the EMF from radio technology B from operator B, and so on and so on. So that means we need to identify the EMF from one single technology from one specific operator. Now let's have a look into 5G from the technology part. Why is 5G challenging in terms of EMF exposure? First, 5G is offering beamforming. That means we have directive antennas looking into certain directions. Later on more on this. Second, and this is a big challenge in 5G, we do not have anymore a reference signal that is spread over the entire channel bandwidth. So the only signal that we can use as an always-on signal in 5G is our SSB, the synchronization block that you know. So this 240 sub-carrier bandwidth, and this bandwidth is somehow narrow compared to the entire channel bandwidth in 5G. Unfortunately, the traffic in the resource blocks besides the SSB depends on the traffic situation. So we are packet switched. So I cannot do a simple linear extrapolation from the SSB bandwidth into the entire channel bandwidth of 5G. So we have to take some assumptions and some considerations for that. Another aspect is the beam forming in 5G. So typically, like shown here with the different colors, in my picture, the SSBs, so the synchronization blocks, are mapped on different beams sent in different directions. But this is only for the SSB. And now what about the traffic? Maybe the traffic uses the same beam as the SSB, or maybe the traffic uses an alternate beam. Here the blue color, the dark blue color beam. So then we need to measure a signal, but unfortunately there are reference signals contained in the traffic channel that are user equipment specific. So they are flexibly configurable. So that means from a test scenario, we don't know how they look like and where they are. So we cannot use the code selective measurement. We have to do some extrapolation under some theoretical discussions. I will explain later on a few scenarios that I learned. Also, I think this is easy in 5G, we have a TDD configuration in 5G. So there's uplink and downlink in the same timeline. Yeah? So downlink slots and uplink slots. So that means for EMF exposure, I have to perform a gated measurement to only trigger into the downlink direction, for example. And 5G is, as many of you know, in the first deployment using a multi-link, that means NSA mode, LTE in combination with 5G. So then maybe talk to the regulator. We may need to measure the EMF on both technologies and combine the values. So that means I need to be able to measure the EMF exposure from LTE and combine it with the EMF exposure on 5G. So now what are possible requirements I learned from certain regulators worldwide? For example, some regulators, they say, take it simple. In 5G, we only want to verify the general exposure. That means we do a spectral scan in a certain bandwidth, and we measure the EMF exposure within this bandwidth. So every signal that contributes, this could be the serving cell, the neighbor cells, another operator, everything that is visible with this band contributes to the EMF. Yeah? On only, let's say, we should not trespass a limit. Other regulators, they propose the following because they know that 5G traffic is fluctuating, it's packet switched. So therefore they would like to assume a kind of full loaded cell, but we cannot force the base station, the cell, into a kind of test mode. So then they propose a time averaging. For example, you see here the ICNIRP organization, they suggest a 6-minute averaging time, or even IEEE, another organization, for example, they propose in some papers an averaging time of 30 minutes. Yeah? Another example I learned from some regulators, they try to emulate a kind of worst case condition. So with real measurements, they scan the SSB, the synchronization block. But this is what they measure on the peak. So like here in my figure in the slide, you see they measure the SSB on the green color, so on one beam. This is the strongest beam detected at this measurement position. But then we know that we have to extrapolate into the wide channel bandwidth, and therefore they propose here in this formula, you see here this parameter alpha. And alpha is a kind of correlation factor, a theoretical value that takes into account the total antenna gain, so what I know from the data sheet, versus the antenna gain of the SSB. So in this case, they extrapolate into a worst case condition. On another procedure, they suggest a kind of 5-step proposal to do a spectral EMF measurement in 5 steps. So like do a quick scan on the overall spectrum to locate the SSB burst, based on resolution bandwidth settings. Then we obtain a kind of histogram. This is the propagation of the traffic, how the traffic propagates and behaves. And optionally, at the end, we can do some kind of post-processing. That means a kind of adaptation and correction of the measured values by some theoretical calculated correction factors. Yeah? A more complex procedure for EMF measurement is what I learned from a regulator. And this regulator, for example, they try to emulate a worst case condition in 5G. So what we see on the left and up, this formula, it's the E, so the electric field, and here we have to measure the maximum. The maximum is obtained by measuring at different positions around the base station site, for example, by measuring all the SSB signals that are visible and integrate them, here the sum symbol, and integrate them all together. And this measurement result, E, is now multiplied with the parameter K, the K. And this K is an extrapolation factor that is then further divided into different adaptation factors. For example, there is an extrapolation factor taking into account the permitted power versus the beam configuration. We have an extrapolation factor of the antenna itself, and we have an extrapolation factor taking into account the TDD and FDD, so the uplink downlink configuration, and also the options that we may have a beam that is fluctuating. So some more details on this procedure, for example, is first, the requirement is to measure all the SSBs that are visible at one single measurement site. So here we see the sum. So our test equipment needs to integrate. So to measure the SSB indices all at the same time and then integrate all the SSB powers to one single value together, and also to do a kind of peak search analysis to detect the strongest EMF here. A second is the correlation factor that takes into account the certain beam forming behavior. So what is shown in that slide is the blue color. The traffic channel beam maybe points into another direction as the SSB beam, and also what is possible in theory that the antenna gain of the traffic channel beam is a different gain compared to the SSB gains. And this is then taken into account with this correction factor, where we take into account the worst case, so the datasheet maximum power, which is this value Pi permitted. And this is what is set in relation to the power measured on the SSB. And even more difficult, sorry, this slide, there's lots of formulas, is an antenna correction factor that takes into account the different antenna radiation pattern of the SSB pattern versus the traffic or general antenna radiation pattern. For example, you see here the direction 1. Here the SSB is at the maximum of the antenna pattern, and also the traffic channel is also measured at the maximum. So that means we don't have to correct something, so antenna correction factor is set to 1. If you take a closer look, for example, in direction 3, which is on the right and down in direction 3, you see that the traffic, the general antenna radiation pattern, has a higher gain compared to the SSB gain. So the SSB is attenuated. And therefore we need to correct because we want to emulate a worst case condition. And this leads then into an antenna correction factor which is bigger than 1. Or even another position is direction 4. That means I perform my measurement at the wrong position. Yeah? So I'm looking into a side lobe or into the backyard of the antenna and not into the main directions. So my measurement results are not plausible and realistic anymore. And this will then be corrected. In this case, I have to substitute my measured results and take a complete different antenna correction factors on that. Yeah, so you see, there is no single solutions for EMF measurement. And also for ROHDE SCHWARZ, now we need to provide different solutions how we can do test and measurement for EMF. What are our solutions? The solutions we are providing is using our test equipment, a network scanner, the TSME. So ROHDE SCHWARZ clearly positions itself, and we propose for EMF in 5G the code selective. So our suggestion is to measure the SSB, the synchronization block, as the reference signal to measure the power, and therefore we have a network scanner, the TSME, that is used normally in drive tests to perform network measurements, coverage measurements. To control the scanner, we have developed functions on our QualiPOC software, which is an application on the smartphone, and this application controls the scanner. Nevertheless, I can also use the ROHDE software together with the scanner, or we also have a frequency selective measurement possible. So we have our spectrum analyzer portfolio. And here, for example, I can use the handheld with an isotropic antenna to perform the spectrum frequency selective measurements if the regulator says. So here, more details on this code selective 5G EMF. We're using the TSME, which is the fastest scanner and the highest accurate scanner that we can get. Yeah? And this scanner is able to measure multiple SSBs in 5G on multiple frequencies in a very fast time. To control the scanner and to have an easy graphical user interface, we use the QualiPOC software, and just as an example, here you can see the EMF value already and easily displayed in the software in the screen of your smartphone. We combine the scanner with antennas. For example, here 2 antennas, like the top one is an omnidirectional antenna with certain known characteristic, or we can also use a kind of directive antenna. You see here on the lower part of the slide, a kind of directive antenna that allows us to connect these antennas to the scanner, TSME, and to perform 5G EMF measurements. Another option is, of course, to use the TSME with the software ROHDE. ROHDE is developed for drive testing. It's a very powerful software which gives me a lot of information, and of course we include the EMF values also measured in the ROHDE software. Yeah? But the point is, if you only need to measure EMF and you are not interested in like benchmarking, in network quality analysis, in interference measurement on your real network, in addition to that, if you only need to measure EMF measurements, then we can do the easy way and just use a smartphone, yeah, instead of a PC, which has more processing power. So ROHDE is possible for those customers who use already ROHDE. And last but not least, we can also offer the spectrum, the frequency selective EMF exposure. And this is done, shown here is with a few photos, for example, with our today handheld spectrum analyzer, FSH or Spectrum Reiner FPH. They have a bandwidth up to 20 megahertz. Or we will offer the front-end remote radio head, the NRQ, which has a bandwidth of 100 megahertz, combined with, for example, an isotropic antenna. And this gives you the full 5G 100 megahertz channel bandwidth in FR1 to perform EMF exposure. Yeah? So that's about some aspects in 5G, EMF measurements. You know, details matter. It's worth to wait to get it right, but we hope that we have the right solutions for 5G EMF measurements. Thank you for your time and stay tuned. Goodbye.